which I told you about briefly at the end of the last lecture, which is trying to obtain Lyapunov exponents for quantum systems. So before we go to quantum systems, let's look at what the important concepts are as far as chaos and Lyapunov exponents are concerned in classical system, at least those concepts which will be important for us when we look at quantum systems, what the corresponding concepts are in classical systems. Okay, so the idea is that imagine that you have some classical system, by which I mean that there are some coordinates, or if you like even more correctly, some variables which can be grouped into canonically conjugate pairs. So I'm thinking implicitly right now of a Hamiltonian classical system. Of course, it doesn't have to be a Hamiltonian classical system. Chaos in any classical deterministic system can be defined much more generally in terms of just variables evolving as a function of time or some other parameter. But just to set the stage for what we're going to do when we look at quantum systems, let's just think of classical systems in which you have conjugate pairs of coordinates and momenta, and you identify a momentum conjugate to a particular coordinate by looking at the Poisson bracket between these two variables. And if these are indeed canonically conjugate pairs, then the Poisson bracket is going to be equal to 1. Otherwise, the Poisson bracket is equal to 0. Okay, anyway. So now the point is that imagine that you have such a system, and let me just very generally call the combination of coordinates and momenta, the entire set of variables, some set xi. So I goes over all the coordinates and all the momenta. So instead of calling them p and q, I'm just calling them all x. And so then what you have is you have the notion of a phase space, which is, so imagine that there are n such variables, so n by 2 coordinates and n by 2 momenta. And so your phase space is an n-dimensional space in which the evolution of the system can be represented. And so, schematically, you can think of this n-dimensional space as something with n mutually perpendicular coordinate axes. And so it's say something like this, and you have x1, x2, x3, and so on, and xn. So this is just some representation on the board of an n-dimensional space. And then the way that the evolution proceeds is that you have some initial state of the system, which is represented as a point in this phase space. And then there are some equations which tell you how these coordinates evolve as a function of time. And so then the evolution of the state of the system is given by some trajectory in this phase space. So that was a setting in which you look at chaos in sort of dynamical Hamiltonian systems, or at least the evolution of the system. Now, this phase space point is something which contains complete information, complete classical information about the system. So just like in the previous lectures when we were looking at these classical spin systems, and we said that the components of the spins, all the components of the spins at any given point of time contain all the information about the classical system. Here, of course, the equivalent objects are these variables, and so if you know all of these variables at any given instant of time, you have all the information possible about the system, because any other sort of meaningful information is contained in quantities which are some functions of these. And so at every instant of time, graphically, all the information is contained in whatever is the phase space point depicting the system at that instant of time. So now again, within sort of the same framework, the notion of chaos basically comes from, at least that notion of chaos that will be important for us comes from looking at trajectories which start out at initial points which are very close to each other. So you take one initial point which is here, another initial point which is there, and then you evolve the system starting from both of these initial points. And if you see a divergence of the trajectories as time progresses, so if you actually look at, so the simplest thing that you can do is you can look at the Euclidean distance between the points on the two trajectories at any instant of time. So by which I mean that you look at d, which is square root of summation of I going from 1 to n, xi a of t minus xi b of t whole squared, where a and b are the two trajectories. So let's say, and this is a function of t, trajectories. Okay. And so generally, the notion of chaos comes from d of t, this distance, increasing exponentially with time with some coefficient lambda. Now, there are many things to qualify here. So first of all, you could say, well, even if this happens, this particular coefficient lambda could in principle depend on what the two initial conditions were, right? So, it could depend on whether the two initial points that I've chosen are here in phase space or there in phase space or there in phase space. In all of these cases, if the system is generically chaotic, you will find an increase of this sort. But then this quantity lambda, which is called the Lyapunov exponent, but then in principle, it could be dependent on the initial states. And so if you want to get a value of lambda, which is not dependent on which is not dependent on the initial state, then the simplest thing that you can do, the most unbiased thing that you can do, is to sample over all of phase space. So you basically look at, in some sense, all possible pairs of infinitesimally separated initial states, and then average over all such possible states over all of phase space. And then that would give you something, assuming that, that also when you do the averaging, and so you calculate d of t for each one of these pairs, and then you average over all of these d of t's, and assuming that that average also goes as the exponential of time, you can now pull out a number which has no dependence on the specific initial states that you consider. Another reason for doing this is that there could be special points depending on the system where you could have, I think Leah Santos in her lectures mentioned something about the inverted pendulum, and she said that the inverted pendulum is an example of a system which is fundamentally not chaotic, but if you were to try to calculate a Lyapunov exponent starting from a very special kind of initial condition, then you could actually see some exponential divergence of trajectories. And that really is something like, if you take the inverted pendulum, so the inverted pendulum is just, so the simple pendulum, let's say, is something whose stable equilibrium position is with the pendulum hanging freely, making an angle of 0 degrees with respect to the vertical. And so now imagine that it's at 180 degrees with respect to the vertical. That point is also a point of equilibrium, except that it's a point of unstable equilibrium. So now imagine that your initial state is basically just that point, okay? So then, of course, the system doesn't evolve, nothing happens. It's unstable equilibrium, but it's equilibrium all the same. So the pendulum, if you started from that point, is not going to move at all. But on the other hand, if you give it even a tiny displacement, or even a tiny velocity, because it's an unstable equilibrium point, you know that it's going to move, right? And in fact, it's going to follow some trajectory. And so if you look at the divergence of trajectories in this very special case, where one of the initial points is this unstable equilibrium point and the other one is slightly displaced away from it, of course, you're going to see some kind of divergence of trajectories, which actually at small times is going to look exponential. But that's because this is a special point. If you were to start the pendulum out from any other point in its phase space, this inverted pendulum, this pendulum, and then if you were to start it out from some any other point, trace the evolution of its trajectory, start it out from some other point which is infinitesimally close to this one, and trace the evolution of the trajectory, you would actually see no such exponential divergence, because a pendulum with 1 degree of freedom and a Hamiltonian is fundamentally not chaotic. So that's another thing which is useful for you to know in case you don't, that if you take a classical system with 1 single degree of freedom, with 1 position coordinate, like this pendulum, and if it is described by a time-independent Hamiltonian, then the system is not chaotic, because it has as many conserved quantities as it has degrees of freedom. So if you have as many conserved quantities as degrees of freedom, then the motion is too constrained and it's not chaotic. Okay, so the reason I bring that up is that in more complicated systems, you could have special points in phase space where the behavior could be different from the generic behavior elsewhere. And so, for instance, you could in principle see some kind of exponential divergence when there's no exponential divergence, or maybe even some exponential convergence where generally there is no in general exponential convergence. But usually all these special points are just special points in phase space. Together they make up some set of measure 0 usually. So when you average over all of phase space, you at least get rid of any special unusual behavior coming from these points. So that's another reason to average over all of phase space. There are times when you don't literally perform an unbiased average over all of phase space. You can actually average over phase space, but with some distribution over the initial points. For instance, if you think of the system now being connected to a heat bath, that distribution could be provided by the bath. It could be some canonical distribution. So these are all different conditions under which you can calculate this Lyapunov exponent. But anyway, that's the idea, that this is how you calculate a Lyapunov exponent, by doing some kind of average over phase space. All right, so this, okay, but now you can actually break this up into something that's a little more descriptive. So if you're just looking at the Euclidean distance between these trajectories, then what you're not specifically looking at is how individual coordinates are diverging from each other as a function of time. So for instance, I could equally well ask the following question, which is that if, let's say, the two initial conditions had a certain separation of delta x j in the jth coordinate, then after a time t, by how much is the ith coordinate separated between the two trajectories? So if the initial separation between the jth coordinate is delta x j of 0, I can ask what delta xi of t is, and I could be the same as j, it could be something else at time t. And so generally, again, in generic chaotic systems, what you would expect to see is that delta xi of t by delta xj of 0 in the limit that this is going to 0, that these individual coordinates would also generically, and again, I keep using the word generically, have some exponential divergence. And then if you were to calculate that lambda which I've written there, and if you have this kind of divergence, or this set of Lyapunov exponents with the individual coordinates, then what's going to happen is that that lambda is typically going to end up being the largest of these lambda ij's, right? Because what will happen is that if you were to calculate the Euclidean distance is basically the sum over the squares of the separations of the individual coordinates. If, let's say, all of them have some exponential dependence on time, ultimately at long times, the one which is going to dominate is the one which has the largest positive lambda ij. Okay? So in general, you could say, at least for our purposes, that if you were to calculate these quantities And if you find that there is, some lambda ij which is positive for some pair of these coordinates, then the system is chaotic, and that's also going to show up in your calculation of the Euclidean distance.
In your numerator, that should be I, right?
Sorry?
In your numerator of the expression. The numerator of your expression, that should be xi, delta xi.
The numerator of that expression, there should be x.
Delta xi.
Oh, I, okay, sorry, I think I might have meant to write I and ended up writing, no, okay, so actually the denominator should have an I. The numerator should have a j. At least in, what I've written there, to be consistent with that. Sorry, yeah, no, it's the other way around, you're right, I and j. Delta xi of t by delta xj of 0. Thank you. Okay, so let's say that you're interested in these individual Lyapunov exponents, lambda ij. So then you would say, well, let's just average this quantity over all of phase space. Just like here I was saying, you could do this for the Euclidean distance. And so you average this over all of phase space, and then you get some lambda ij, which is now not dependent anymore on some specific initial conditions. But that's not actually what you do. So if you average this object, then it could happen that there could be cancellations from different trajectories, giving you 0 or something that's not exponential, because you could imagine, for instance, starting the system out with in sort of two different initial conditions which are very close to each other, and then the trajectory is diverging like this, or two other initial conditions very close to each other somewhere else in phase space, where the trajectories diverge, but they diverge like that. So then in one case, what could happen is that this quantity could be a positive number. In the other case, it could be a negative number. In both cases, of course, it would increase exponentially, but you could have this cancellation in principle between positives and negatives, and could give you some, and that cancellation could actually give you something which doesn't have this form. And so to get around that, the proper quantity to look at is just the square of this object. And so when you do that, then, and you average, and if that increases exponentially, then you say that you have chaos in that particular pair of coordinates. And so just following the convention of this notation, when you put the square and you average, you also put a factor of 2 here. And so that's how you extract the Lyapunov exponent for this particular pair of coordinates. So this is actually interesting because this is going to be our starting point in terms of generalizing this notion to a quantum system. So the quantity of interest is going to be this. Again, delta xi t. Okay, and so the limit. And so this can be written as the square of this partial derivative. Now this form is actually a very useful form, because what it allows us to do is to express this quantity in terms of Poisson brackets. And so the way that we do this is the following. So remember that I assumed right at the outset that this was some system in which you had pairs of conjugate momenta and coordinates, and that's what these x's are. And so now if you look at a quantity like this, if you look at delta xi t, delta xj 0, and these are coordinates or momenta, then this quantity can actually be written as the Poisson bracket of xit, and let me just call this xj bar 0, where xj bar is conjugate to xj. So let me write this down and then I'll explain what I mean by this. Okay. So all of you are familiar with Poisson brackets in general. We've talked about Poisson brackets even in the previous lecture. And so if you have a pair of canonically conjugate variables, say Q, some set of canonically conjugate variables Qi and Pi. Okay, let me actually write it like this so that you don't confuse it with the set of Qi's and Pi's. Then the Poisson bracket between two quantities A and B, which are functions of Qi and Pi, is just defined as summation over I del A del Qi del B del Pi minus del A del Pi del B del Qi. Okay? So you can ask, well, how do I know for a system what the canonically conjugate variables are? And then I told you right at the outset that, well, you calculate the Poisson brackets between the canonically conjugate variables, and if they turn out to be 1, then they're canonically conjugate, otherwise, they're 0. But then in order, so you can see that it's a slightly circular argument here, because in order to calculate the canonically conjugate variables, I need those variables in the first place to even define the Poisson bracket. So the way that I can go about doing this is that I can first define a set of variables as canonically conjugate, no questions asked, by construction, and then proceed to look at other variables defined in terms of these, and then decide whether those variables can also be canonically conjugate. And the whole point about, and the great thing about a Poisson bracket is that when you're calculating the Poisson bracket between any two quantities, it doesn't matter what set of canonically conjugate variables you're using. Any set of canonically conjugate variables will do, and one set of canonically conjugate variables can be related to another set of canonically conjugate variables through something called a canonical transformation, which you're all familiar with. Now, if you take a Hamiltonian system, right, and you have those variables xi of t, in principle, of course, you know that xi of t can be written in terms of the initial conditions on these variables, right? So if you specify a set of initial conditions, then I can, of course, get the final values of xi of t in terms of those initial variables. What is a little less obvious, but is true, is that if I've identified the canonically conjugate pairs among the xi of t, then the corresponding initial conditions, the variables in the initial conditions, are also canonically conjugate pairs. So therefore, xi of 0, the set of xi of 0 split into coordinate and momenta, will also form a set of canonically conjugate variables, just like xi of t do. And so I can define a Poisson bracket with respect to the initial variables, xi of 0, and that's exactly what I've done there. So if you look at this expression, right? So del xi t del xj0 can also be written as del xi t del xj0 times del xj bar 0 del x j bar 0 minus del x I t del x j bar 0 times del x j bar 0 del x j 0. So this quantity is equal to that quantity. And why is this quantity equal to this? Because the first term is just this quantity itself. This is just equal to 1. Now if you look at the cross term, because I've told you that these initial coordinates were canonically conjugate, so xj bar is canonically conjugate to xj, and so therefore this derivative is equal to 0, and this term is equal to 0, and so I can write this in this way, and you can see that this object that I've written here is nothing but this Poisson bracket. And so therefore the derivative that I have here, whose square I'm taking and then averaging, is nothing but the Poisson bracket between this variable and the conjugate of the other variable. Okay, so that's nice. For a classical system, perhaps, it's nice, but it's maybe not spectacularly useful, because for a classical system, one could also calculate the Lyapunov exponent by simply looking at phase space trajectories and calculating the Euclidean distance between them. When I say simply, it may not always be all that simple to do this analytically, but at least numerically, it's a well-defined thing, and indeed is routinely done. But it turns out that for a quantum system, that is, as I mentioned at the end of my last lecture, that is not something that's a well-defined procedure, simply because of the lack of a well-defined phase space, right? And so if you have to find some equivalent method of calculating the Lyapunov exponent for a quantum system, then there has to be some other way of generalizing the notion of a Lyapunov exponent for a classical system to a quantum system. And the other way of doing it is actually through the Poisson bracket, because as we've discussed earlier, we know how to extend the notion of a Poisson bracket to a quantum system by first raising these quantities to the level of quantum mechanical operators and then replacing the Poisson bracket by a commutator. Okay? So that's going to be the strategy. And so, right, okay, so coming back to this anyway, so still staying in the classical realm. So what we are now saying is that we expect that xi of t, x j bar of 0 whole squared average is going to go as some e to lambda I j t. Now, it turns out that in general, again, generically for a chaotic system, it doesn't even have to be these canonical positions and momenta that you need to stick in here in order to see some exponential divergence with time. If you take generic functions of these x's, let me just call them w and v. So if I look at some w of t and v of 0, where w and v are some functions of these xi's and xj's, then generically even this is expected to have some exponential increase with time when you average suitably over phase space. And what's going to happen is that, again, for some very generic w and v, the lambda that you pick up here is actually going to be the largest Lyapunov exponent in the system, meaning the largest of these lambda ij's for pairs of these canonical variables. And that's because if you were to just at random pick some w and some v and then write these out as functions of these x's, there is, if these are truly random, there's nothing special about them, they're also likely to be functions of that particular pair of xi and xj, which is going to have the largest lambda ij. And so if you were to look at the evolution of this Poisson bracket as a function of time, eventually it's going to come to be dominated by the largest lambda. Okay, so this is sort of a generic statement. Anyway, so now there are sort of two things that I wrote down, and because I went over them quickly, maybe one of the things that you didn't immediately realize is that even though I've sort of defined the Lyapunov exponent, I have effectively defined it in two different ways. Okay, so one way of defining the Lyapunov exponent was looking at the Euclidean distance between trajectories, and then what you do is you calculate the Euclidean distance between trajectories for all the different excuse me, calculate the Euclidean distance between trajectories for different points in phase space, different pairs of very closely spaced initial conditions for different such pairs. You calculate the Euclidean distance, extract a Lyapunov exponent for each of those pairs, and then average over those Lyapunov exponents. The other thing that you can do is, instead of averaging over the Lyapunov exponents, what you could do is you could either calculate this or equivalently that quantity, average that over phase space, okay, and then say that that is equal to the exponential of some 2 lambda t, and then extract the Lyapunov exponent this way. And the difference between the two ways of doing this is that in this particular case, what you're doing is you're actually averaging over a bunch of exponentials. Each one of these trajectories, the each one of these quantities for a particular pair of phase space points is itself going to go as some exponential over lambda t. You're averaging over all of those exponentials and saying that that is equal to the exponential of something, and from that you're extracting the Lyapunov exponent. Whereas in the other case, what you're doing is you're actually extracting the individual Lyapunov exponent for pairs of trajectories, right? And then averaging over the Lyapunov exponents to get a Lyapunov exponent. So is that clear, or do you want me to go over that again? And there's no guarantee that these two things are actually the same, and in fact it turns out they're not the same. They are different, and I'll just show you an example of them being different. Now, the reason that I bring this up is that it turns out that the procedure of averaging over the Lyapunov exponents to get a Lyapunov exponent is something which in certain cases can be carried out analytically or semi-analytically. On the other hand, this procedure, as far as I know, is not very easy to carry out analytically. However, this is the procedure which has a natural extension for a quantum system. And so when one is calculating a Lyapunov exponent for a quantum system, one has to be mindful of the fact that it's really this lambda that you are calculating and not the lambda for the corresponding classical system that you would have got from averaging over the Lyapunov exponents. And so I'll go over this point with a specific example in just a little bit, but I thought I'd mention this. Okay, so now having sort of defined in some sense the Lyapunov exponent and also gone over how you would calculate this object in specific, by averaging over phase space, let's now look at a specific system for which these kinds of calculations have been done. And in fact, this particular system in some sense is like a prototypical chaotic system that people study. And this is all classical at the moment, and I'll show you the quantum equivalent of the system in just a minute. So the system in question is something called a kicked rotor. Okay, so what is this kicked rotor? So the kicked rotor is actually a system with just one single degree of freedom and a Hamiltonian. And then you would say, well, you just told us just a short while ago that a system with one single degree of freedom and a Hamiltonian is not chaotic. That is true as long as the Hamiltonian is time independent. So as long as you have a conserved energy, the system is not chaotic, because then you have as many conserved quantities as numbers of degrees of freedom. But if you can make the Hamiltonian time dependent, then the system can become chaotic. And so that's exactly what the kicked rotor is. So the kicked rotor has the following time dependent Hamiltonian to describe its dynamics. And so in some dimensionless units, it has the following Hamiltonian. So let me write this down, and then I'll tell you physically what the system does. So that's the Hamiltonian, okay? And you can see that there is this time dependence coming from the sum over delta functions. J here is an integer which goes from minus infinity to plus infinity. So if you want to think about the system physically, think about some object which is like a rigid rod, and let's say the rod is constrained to move. It's rigid, it's constrained to move only in the plane of the board, and one side of it is fixed. So it has only one degree of freedom, which is basically its orientation with respect to some x-axis, and that is the variable that I'm calling x. You could also call it theta if you like, if you're not comfortable with calling an angle x. The reason that it's called x here is that usually when this particular system is studied, this quantity x is not a priori assumed to be a compact variable, something which goes only from 0 to 2 pi, and so you call it x. Of course, its action in the Hamiltonian ultimately is that of a compact variable because it's in a trigonometric function. So that's x. P here is the canonical momentum, which for this particular, if you look at it this way, is really the angular momentum of the rod in the plane of the board. So that's all the system is. It's a rigid rod which can only move in a two-dimensional plane and thus has this 1 degree of freedom. So now you can see that from the Hamiltonian that there's a kinetic term and then there's also a potential term. So what the potential term tells you is that as the rod is moving, it actually feels a potential. It's not rotating freely. However, that particular potential switches on only at specific instants of time, which are all equally spaced. So it's only at specific instants of time, not even intervals of time, the specific instants of time at which the rod feels the potential. At any time other than those instants of time, the rod is just rotating freely. There is no potential that it feels. And so every time it feels the potential, every time t is equal to an integer in these units, it feels the potential and it receives a kick. And so it turns out that this system, this fairly simple kind of system, can actually go chaotic, can actually have an exponential divergence of trajectories in the p and x phase space if your kicking strength k is sufficiently large. And so there is a critical value of k, which I'll call kc, such that for k greater than kc, the system has a positive Lyapunov exponent and it's chaotic. And for k less than kc, it does not display chaos, so not chaotic. And so your Lyapunov exponent is 0. Okay, so this is a prototypical, one of the sort of standard chaotic systems that is studied in the field of dynamical systems.
I have a question. So is this some
Yeah.
Is this somewhat diluted version of this Cherenkov map?
Yeah, exactly. So I was coming to that. It is exactly the dynamic. So if you discretize this, it is your standard Cherenkov map. So since you mentioned the since you mentioned the Cherenkov map or Cherenkov, so it turns out that one of the great advantages of studying this model is that in a certain limit, you can actually calculate the Lyapunov exponent for this for large values of k semi-analytically. You actually have a semi-analytic expression for the Lyapunov exponent for very large values of k. However, for the Lyapunov exponent as defined by averaging over Lyapunov exponents for individual trajectories, as opposed to averaging over the exponentials and pulling out the exponent. Okay, so just to make that point a little more precise, let me just show you some numerical results here. Okay. So these are calculations for the quantum version of this, which I'm going to come to in just a minute. But for the time being, ignore the quantum version. So look at this particular plot here. So you can see that there is a lambda and a lambda tilde, which have been plotted as a function of k. So k is the kicking strength. And I'd like you to focus on these two curves. So the curve that's given here by the dark green line, the one which is called classical CGR, and then there's also the other curve which is given by the blue open diamonds, which is called classical LE or classical Lyapunov exponent. So the classical LE is what is called lambda in this paper. The classical CGR is what is called lambda tilde. Lambda is the one for which, you calculate the Lyapunov exponent by first calculating the Lyapunov exponent for individual trajectories and then averaging over them. The CGR, on the other hand, is the one for which you calculate that object for different initial conditions and then average over phase space and then set it equal to the exponential of something and extract the exponent. That is lambda tilde. And you can see that lambda and lambda tilde are not the same. So there is actually a difference between lambda and lambda tilde. And in fact, as you go to larger and larger values of k, that difference essentially becomes constant. And I forget what it is, but it's something like log 2 by 2 or something like that. So these two objects are not exactly the same. So mind you, there's nothing quantum mechanical about this. I'll come to the quantum mechanical calculation in just a bit. The quantum mechanical version of this, those numbers are given by these by the data in these circles, which we haven't come to. So all of this is still classical. And so these two Lyapunov exponents are not the same. And since we mentioned Chirikov, so this exponent lambda actually has, as I said, a semi-analytical expression due to Chirikov, which works well for large values of k, and that is this dashed line. And so you can see that the dashed line nicely fits these blue triangles. But then what happens is that you know finally that this, that below Kc, k equal to Kc, you actually should get a Lyapunov exponent of 0, which is indeed happening with the numerical data. But if you look at the semi-analytical form, that doesn't go to 0 at k equal to Kc. In fact, it doesn't go to 0 anywhere. And that's because this Chirikov semi-analytical formula breaks down once your k is not very large. The other interesting thing to notice here is that if you look at lambda prime, which is the object that you are calculating from there, lambda tilde rather, lambda tilde doesn't seem to go to 0 at any value of k, but lambda does. So what's that? So what that's telling you is that this other object which you're calculating, while it might be useful in terms of actually getting a Lyapunov exponent, is not particularly useful for looking at the transition between a chaotic phase and a non-chaotic phase. For that, it's really the other exponent that you should be calculating, and that was the one which is difficult to calculate quantum mechanically. It's not very efficient calculating that quantum mechanically. So this is something to just keep in mind, even as far as the classical system is concerned, and looking at the distinction between these two definitions of the Lyapunov exponent. Okay, so now let's go to the quantum mechanical version of this model and also generalizing that formula to a quantum mechanical system. And so the generalization of that formula for a quantum mechanical system starts with looking at the equivalence between Poisson brackets for a classical system and commutators for a quantum mechanical system. So classical mechanics, if I have the Poisson bracket between two objects A and B, then the corresponding quantity quantum mechanically is 1 over I h bar times the commutator between the corresponding operators quantum mechanically. Okay. So given this, if you now look at some quantity like the one that I'd written there, the Poisson bracket between two classical quantities W of t and V of 0, then the quantum mechanical version of this would be minus 1 over h bar squared times the square of, okay, so let me just write the square here. So the square of this Poisson bracket, if you look at the quantum mechanical version of it, it would be minus 1 over h bar squared, the square of the commutator between the operators W hat of t and V hat of 0. Okay, and so the equivalent of this object, the phase space average of this quantity, would be a suitable average, and we'll come to what suitable means, of the square of this quantum mechanical commutator. And so this object here is what is called an out of time ordered correlator, or OTOC or OTOC for short. And so the thing which allows us to make this classical to quantum mechanical correspondence is really the Poisson bracket. The fact that the quantity of interest classically, which you want to calculate, could be expressed as an average over phase space of the square of a Poisson bracket is what has allowed us to write down an equivalent expression for the quantum mechanical system in terms of these commutators. Okay, so now you can ask, well, what is the thing that you're averaging over here when there is really no phase space in for a quantum mechanical system? So then what you could do is you could look at what would be the equivalent of phase space for a quantum mechanical system. So remember that when you think of a classical system and you think of phase space, as we discussed earlier in this lecture, a single phase point at time t gives you all the information that you can get about the classical system. So you can now ask, if you're given a quantum mechanical system, what is the object that can actually give you all the information in principle about the quantum mechanical system at any time t? Okay, and so that object is nothing but the state ket of the quantum mechanical system, or if you like, the wave function of the quantum mechanical system. Because if you know that, then in principle you can calculate the expectation value of any observable, any operator that's defined in the Hilbert space of that system, just from knowing what the operator is and what the state is. And that's all the information that you can in principle extract about the quantum mechanical state. So the first thing is that phase space points for classical systems are equivalent to state kets in the Hilbert space of a quantum mechanical system. So you can then say, well, if I have to perform an average over something suitable for the quantum mechanical system, it would be some kind of average over this Hilbert space, some kind of average over the states of the state kets of the quantum mechanical system, which would be like the phase space average here. I could in principle average over the entire Hilbert space. I could average over some distribution that is given on the Hilbert space. And so, by the way, distributions that are given on the Hilbert space are basically what you call basically things that are called mixed states. Those are the things which are described by density matrices. And I'm guessing that you've already been exposed to density matrices not just in this school, but also in some quantum mechanics course that you've taken. And so you can then define a suitable ensemble on the Hilbert space through a density matrix or density operator, which you can use to calculate this. But the interesting thing about a quantum mechanical system as opposed to the classical system is that it turns out, and we look at the reason for this in a slightly different way in one of the subsequent lectures, that for a quantum mechanical system, you could also choose a single quantum mechanical state as opposed to averaging over the entire Hilbert space, or with some distribution, or averaging over the entire Hilbert space. You could also choose an individual quantum mechanical system, an individual quantum mechanical state, and do this calculation for that state alone, and still get a Lyapunov exponent, which is representative of what would happen if you average over the entire system. And that's because of the fact that for a quantum mechanical system, a generic state in the Hilbert space is actually like an ensemble of states as opposed to just a single state for a classical system. Okay, so right now I'll just leave you with those words without really going into a great deal of detail about what I meant by that. But we will see some manifestations of this even in other contexts when we look at thermalization. So the message from this is that as far as the quantum mechanical calculation is concerned, you can choose to do this calculation in a specific state, provided that specific state is generic enough, as opposed to having to look at an ensemble of states. Okay, so that's how you extend this notion to that of a quantum mechanical system. As far as the specific example of the kicked rotor is concerned, so the quantum version of this would simply be something in which the Hamiltonian remains the same. So it's still p squared by 2I, but now p is an operator, and you have k times cosine of x hat. This is also an operator. And of course, you have the same sum over delta functions that you had for the classical system. But x and p as operators have this commutation relation. So x and p, the commutator is equal to I h bar. So that's the quantum mechanical system. So incidentally, can anyone looking at this make a connection between this system and what Arnab was telling you about in his last lecture? So this is also a nice flow case system. And the reason it's a flow case system is that you can see that the Hamiltonian has a periodicity. It is a time-dependent Hamiltonian, which is periodic with, in these units, a time period of just 1, right? So if I change t to t plus 1, the Hamiltonian remains invariant. So this is a nice flow case system. Of course, it's a much simpler flow case system than the kinds of systems that Arnab is going to tell you about, because his systems would involve many more degrees of freedom. This has just one single degree of freedom. Nevertheless, all the general concepts that he introduced about flow case systems also hold for this. So for instance, there's a flow K Hamiltonian that you can write down, a flow K unitary that you can write down, and you can use that flow K unitary to actually generate the dynamics of the system at specific, at values of t which are integers. So all of that still holds. But for us, the flow K nature of this is not going to be all that important. What is going to be important is the fact that this is quantum mechanical, with x and p now having this relation. Okay, so you can ask, well, how does one go about actually calculating this object now, given some sufficiently generic state in which you want to do it? So first of all, here the quantities that are chosen in that calculation. So what I'm showing you here is actually a calculation for this quantum mechanical system. And so for this particular system, for this particular calculation, W and V have both been chosen to be the momentum operator. And so you've got, for this calculation, W hat is equal to V hat is equal to P hat. And so you're looking at the commutator of the momentum operator at time t with the momentum operator at time 0, the square of that, and then averaged over some suitably, or its expectation value calculated in some suitably generic state. The generic state in this particular case happens to be a state whose wave function is a Gaussian with a certain width. Okay, but that's not particularly important. If this calculation had been done in some other way, you would still have ended up getting the same Lyapunov exponent. Okay, so that's the calculation. Now, you can't do this exactly or semi-analytically. You will have to resort to doing this numerically, which is what has been done in this paper. But now when you do this calculation numerically, there is one thing that you have to know about, you have to be careful about, which is that the numerical calculation literally involves writing down this Hamiltonian as a matrix of numbers, and then hitting the initial state that you've written down with the corresponding unitary. So it's a multiplication of the unitary corresponding to the matrix corresponding to the unitary of the system with a column vector corresponding to the initial state, and then you evolve it. If you want to evolve the state, or if you want to calculate that object, it's the same thing. Each of those operators now is some matrix of numbers, and so you're really calculating a commutator between two matrices, and then calculating the expectation value of that matrix in some particular column vector state. And so because you're doing this, and you're actually working with matrices numerically, there is a dimension of the matrix. And so in order to do this calculation, you have to fix a dimension of the Hilbert space of this system the Hilbert space of the system is actually infinite dimensional. So one thing to keep in mind, and some people do get this confused, is that the number of degrees of freedom doesn't have anything to do with the Hilbert space dimension. So even if you think of the most simple quantum mechanical system, a particle in a box, right? So a particle in a box also has just 1 degree of freedom, but it has an infinite Hilbert space dimension. So similarly, this thing also has an infinite Hilbert space dimension. And so if you are going to do a numerical calculation, then what you're doing is you're limiting the Hilbert space dimension. And so the way in which the Hilbert space dimension has been limited in this calculation is to say that the allowed eigenvalues of p hat. So if you ask what are the eigenvalues of p hat, so p hat being the momentum operator has some eigenvalue equation like this. These are the eigenvectors and those are the eigenvalues. And in principle, the eigenvalues of this could be any rational value, any real value of k. So when you limit and so that would be an infinite dimensional Hilbert space. So the way in which you limit the Hilbert space dimension here is to first is to say that there's a k max and a k min. Oh, sorry, no, there's something here, something which I told you which isn't right. Okay, just 1 second, sorry. Let me just back up. So something which I told you which isn't correct, which is that p hat acting on p is going to be, n h bar acting on p. So I might as well just call this eigenstate n and this eigenstate n. Okay. And the reason for this is that p here, remember, is like an angular momentum. It's like the z component of the angular momentum. If the plane in which this kicked rotor is confined is the xy plane, and so this is like the Lz operator, and you know that the eigenvalues of the Lz operator are of this form, n times h bar, so they are discrete eigenvalues, but n can take any integer value from minus infinity to plus infinity. So that's the way it's an infinite dimensional system, right? And so if you're now going to do an infinite Hilbert space dimensional system, so if you're now going to do the calculation for a finite Hilbert space dimension, then what you do is you restrict n to be between some minus n max to plus n max. So that now gives you a finite Hilbert space dimensional description of this system, because you're restricting the allowed values of n. But the allowed values of n between this range are still in units of h bar. So you still have a discrete number of n values, but you have a maximum and a minimum value. Okay. So imposing a maximum and minimum value for the corresponding classical system, if you like, is like imposing some constraint on the maximum energy that the kicked rotor can have. That you're saying that the maximum allowed value of the momentum for the classical system is not going to exceed something. So at most, it can only have a certain energy, because as Arnav told you earlier in his discussion of flow case systems, what happens generically for a flow case system, and regardless of whether it's a classical system or a quantum system, is that if you have this sort of periodic drive, then what would happen is that the system would keep absorbing energy from the drive and get heated up to infinite temperature, and so basically have unbounded energy. And so classically, the equivalent of doing this is to bound the energy of the system. So in some sense, putting a cutoff on the Hilbert space dimension does have a classical analog. What does not have a classical analog is the fact that the momentum values are discrete. There is no classical analog of that. Okay? So in fact, if you wanted to take the classical limit of this problem, then you would have to take h bar going to 0. And of course, if you also wanted to take the limit of this problem, the classical limit of this problem with the unbounded energy, then you would have to take n max going to infinity. And so these numerical calculations that have been done with different values of n max and also different values of h bar. Now you would say, well, h bar is Planck's constant. How do you have different values of h bar? But as far as this is concerned as a mathematical model, I could, of course, just think of h bar as some parameter, which when it goes to 0, renders that commutator equal to 0 and then makes the system classical. And then as I increase h bar, then the system becomes more and more quantum mechanical. So I could actually investigate what happens to this system as h bar increases or decreases. So all of that is in these plots. So what they've done is they've calculated the out of time ordered correlator numerically for some particular value of n max, which I forget, and I forgot to indicate on the slide. So it's for some, the largest value of n max that they could go to given the numerical resources. So if you look at the first plot, so the C of t here is basically this OTOC, and so this is C as a function of time. Time here is basically measured in integer units. It's those times which are, which are just integers, the stroboscopic times that Arnav was telling you about, because this is a flow case system. So you're just looking at C of t at those specific instants of time at which the potential flashes on. And you see how C of t changes as a function of time for different values of k. And you can see that this here is a semi-log plot. And sure enough, you can see that there is an increase of C of t, an exponential increase of C of t with time. And the larger the value of k, the more pronounced the exponential increase is. And the smaller the value of k, the less pronounced it becomes, which is what you would expect. The system is getting more chaotic as k increases. And you can actually pull out a Lyapunov exponent as a function of k, which is this object lambda tilde here, and that's plotted in this inset here and also here. So this is what I was telling you about. And this is for a particular value of h bar, which they call h bar effective, which is 2 into 10 to the power of minus 14. Here what you have is, so C of t is that object. It's the out of time ordered correlator. So if you opened up the commutator, or if you opened up the Poisson bracket, there would be 4 of those objects, right? So there'd be a W of t, V of 0, and the thing is squared. So that's what's called a 4-point correlator. You could also look at 2-point correlators. You could also look at, for instance, quantum mechanically, the expectation value of W of t, W of 0, or W of t, V of 0. And one of those is what's plotted here. And so the 2-point correlator in this particular case actually reaches a steady state value at about the same time that the 4-point correlator also reaches a steady state value after it has increased exponentially. So the 2-point correlator is actually not going to be very important to us. But what is going to be important is the fact that you have an exponential increase here, and then you have, it looks like the C of t is actually plateauing to some value, like the exponential increase stops at some point. And you can ask, well, and you can see that where it stops has a dependence, of course, on the value of k. But you can ask, why does it stop? Why would the exponential increase stop? And why would you actually have a saturation? And so it turns out that that's an interesting thing, which doesn't really have a proper classical analog. So let me just tell you where that saturation is coming from and what that Sorry, louder?
The out of time ordered correlator you defined there is a measure of something. I don't get a feel for how.
It's a mixture, sorry,
it should be a measure of some distance between two states or some.
Yeah.
Right? So I don't have a feeling for how it gives that.
How it gives what?
How it is a measure of separation between two.
Yeah, okay. So the way that it's, so the way that we even arrived at saying that this is a measure of a separation between two things is first by looking at the system completely classically, right? So completely classically, of course, what we know is that the Poisson bracket can be written as a derivative, which I'd written down earlier. And so the Poisson bracket would then tell you how a particular coordinate is, the separation between the values of a particular coordinate at time t, given a small separation between the values of some other coordinate at time 0.
Yeah, but this is an analog.
But, sorry?
This is an analog, right?
It is an analog.
But,
okay, so the reason that you have to resort to this analog is the following, okay? So it's a good thing that you asked this question. So imagine that I didn't want this analog. Suppose I wanted to look at a straight up separation even quantum mechanically. What would I look at? So classically I told you that what you could do is, you have a well-defined notion of phase space, and in that phase space you have phase space points and you have phase space trajectories. And so if you ask what is actually separating, it's these trajectories which are separating, and you look at the distance between them. So now let's say we want to import this notion to a quantum mechanical system. So the first thing that I told you is that quantum mechanically, the equivalent of the classical phase space point is the state ket of the quantum mechanical system. And so the equivalent of the phase space would be the entire Hilbert space of the quantum mechanical system. So now let's imagine doing the same thing for a quantum mechanical system. Okay. So now let's say I've got my Hilbert space, and I look at some starting state of the quantum mechanical system, which is psi t. Okay, let me say that I look at some starting state psi a at time t equal to 0, and I look at another starting state psi b at time t equal to 0, such that the Euclidean distance between these two states in the Hilbert space is very small. Now you can ask, well, how do I define Euclidean distance on the Hilbert space? So it's actually not difficult to define the Euclidean distance on the Hilbert space. So if you think of this as some kind of column vector in some basis of the Hilbert space, this as some kind of column vector in the basis of the Hilbert space, then you can define the Euclidean distance as the norm of the difference between these two column vectors, right? Or between, so you define it as something like this, right? It's like basically the distance between two vectors, and you know that each one of these is normalized by itself, right? And so if you write out this thing, it's just basically going to be something like the square root of 2 minus twice the real part of psi a t equal to 0, psi b t equal to 0, right? I mean, this is just like saying that if I take any two vectors and I look at the square root of, if I look at the distance between them, this is just a generalization of a minus b, the distance between two vectors a minus b, and that is just a squared plus b squared minus 2ab cosine theta, and that's all that this is, right? So the square root of this. So in this particular case, this is the vector a, this is the vector b, and a squared and b squared are both equal to 1 because these are normalized, and so this distance would be this twice of square root of 2 minus twice real part of this inner product between these two things. So I can then write down the distance in Hilbert space between two states in terms of this inner product, right? So now let's see how that distance would evolve in Hilbert space. If I wanted to actually look at the distance in Hilbert space, starting with two initial states like this, what would happen? So what would happen is the following, that if you ask what that state evolves to, psi a of t equal to 0, psi a of t equal to 0 is going to evolve to a state psi a of t, which is going to be some unitary okay. If your Hamiltonian is time independent, then of course this unitary is just e to the minus I h bar t by h bar. If it is time dependent, then it's the formula that Arnav wrote down, that you have a time ordered product. Nevertheless, it's some unitary. Now we look at what happens to the state that you get from the initial state B. What would that evolve to? That would evolve to this state with the same unitary, right? Because the unitary is independent of the state. So now here's the thing. So if you now wanted to characterize the distance between states using that inner product, you can see that the inner product between psi b of t and psi a of t is equal to psi A of t equal to 0, u dagger t, u of t, psi b of t equal to 0, right? But this is just the identity. And so therefore, you can see that under regular quantum mechanical evolution, the distance in phase space does not change, right? So if you wanted to extend the notion of distance of the Euclidean distance in the classical phase space to the Euclidean distance in the corresponding Hilbert space, and you wanted to characterize chaos that way, you would never see any chaos, right? So that is the reason that you can't use anything quantum mechanically which involves a simple notion of distance in Hilbert space. That is the reason that you actually have to resort to something like this. So it's so again, I'm going a little sort of on a tangent, but the interesting thing about chaos in a classical system versus chaos in a quantum mechanical system is this. For a classical system, what is really giving you chaos is the complicated dynamics. That when you look at the evolution of the dynamical variables, you have several of them, you have complicated nonlinear equations which are describing the evolution, and it's really the complicated nature of the dynamical equations which is ultimately responsible for chaos. If you look at a quantum system, and you ask what is responsible for chaos for the quantum system, if you just look at the way in which quantum mechanical states are evolving, that evolution is actually not complicated. It's this unitary evolution. It's evolution which preserves distances. It's evolution which preserves angles in phase space. So it is not like complicated nonlinear classical evolution, because there's nothing nonlinear about this. What actually is complicated in the quantum case are just the states themselves. The states themselves, quantum mechanically, are much more complicated objects than classical states, as we also saw in the previous lectures, where they could be highly entangled, or they have superpositions and so on. And it's also for reasons like that a single quantum mechanical state can be representative of a very large number of states in the Hilbert space, and so you don't need to do phase space averages and so on.
I understand why not this, but I don't understand why that.
So why specifically that, right? So two reasons. So one is that because it has a natural classical counterpart, which actually does give you a Lyapunov exponent. That's one answer. The other answer is a much more sort of unsatisfactory answer, is in that it works. Okay? It actually does give you.
No, my question was why is it that particular? Why is it that particular quantity? My question was how that particular quantity captures what we want to capture.
Yeah. So it's really, again. So the only good answer for that is through this correspondence between commutators and Poisson brackets. So that's really the only good answer to this, because anything more direct, like measuring the distance in Hilbert space, will simply not work. Distances don't change in Hilbert space. Okay. So anyway, if you're still not satisfied, maybe we can discuss this offline. Okay, fine. So, all right. So I was telling you why there is a saturation of this out of time ordered correlator for this quantum mechanical system. And you might think initially that the saturation maybe has something to do with the fact that we put some bound on the Hilbert space of this, and so because we have sort of bounded the Hilbert space dimension and perhaps then correspondingly even the energy in the classical case, maybe that is causing some kind of saturation. But it turns out that that's not the reason. In fact, the time scale over which the saturation happens is largely independent of the Hilbert space dimension that you have chosen. And so the saturation here is also a very fundamental quantum mechanical effect, and I'll tell you exactly where it's coming from. So let's just go back to the classical system, right, and the classical phase space, and look at a divergence of trajectories in this classical phase space. So here's a phase space point, and you see that there is, some trajectory which starts from this phase space point, and then here's another phase space point which is very close to this, and you have another trajectory which starts from here, and these diverge. And so if this was infinitesimally close to the original point, and if the divergence was exponential, then after some time scale, roughly speaking, you would have a separation between these which would be of order 1. So you're starting out with some separation which is infinitesimal, which is very small, and then you let the system evolve, and you know that the separation is sort of increasing as e to the lambda t. And so beyond a certain t, given by some length scale which is proportional to 1 over lambda, right? You're going to have some separation between these which would be of order 1. When I say this, it could be 50 times this, it could be 100 times this, but it's something which is given by 1 over lambda. Okay, so this is all classical. And classically, of course, phase space points are very well-defined phase space points. Now, if you were to think of a quantum mechanical system, and if you were to forcefully think of it classically in this phase space, not in the Hilbert space, then the best you can do as far as thinking of well-defined phase space points is to think of wave packets, okay? So that's about the best that you can do, right? So wave packets quantum mechanically are the states which come closest to being like classical states. So then if you were to now again, if you want to think in this language but for a quantum system, you start with a wave packet, and remember that a wave packet in this language is not a single point, but it's actually some fuzzy object. Right? So it's not a single point. And now you start thinking of the evolution of this fuzzy object. So because this object is itself fuzzy, it's not a single point, as this object evolves, it itself is going to spread now, if you wanted to think of it in this classical language, as opposed to in the classical case, where a single phase space point is not spreading, it's just evolving, right? So what is sort of diverging in the classical case is two trajectories which both start out at some point, at 2 points which are very close to each other. But here what's happening is that even, in this way of looking at the quantum system, even a single point as it evolves is spreading in phase space. So now imagine starting out with two of these wave packets which are very close to each other, and then letting them both evolve, right? So of course, the mean position of the wave packets will probably diverge. But what will happen is that each one of these trajectories is also individually going to start spreading out. And so what will happen then is that when the width of each trajectory itself gets to be of order 1, then it becomes meaningless to talk about any divergence of these trajectories anymore, because the divergence, if you like, the distance between the mean positions of the wave packets is now of order 1, but each of the wave packets itself has a width of order 1, right? So you really can't think of these two things as being distinct. So you can really think of these trajectories as being distinct only over a time scale which is below the time scale after which the wave packets themselves spread to something which is of order 1. And so if you ask, well, what is that time scale after which these individual wave packets or these trajectories themselves have spread out to be of order 1? Well, so the best you can do in terms of creating a wave packet is to create a wave packet which has a width which is proportional to h bar, right? So, whatever is the sort of in some general sense, right? I mean, that comes from the uncertainty principle. So the best initial width, or rather the smallest initial width is going to be proportional to h bar. If h bar goes to 0, of course, then you could just create a single point, but otherwise you can't. And then if you ask, how does this width increase? Because remember that you're now thinking of all of this classically, but you're actually projecting the quantum system onto the sort of classical picture. Then what's going to happen is that the width of this is going to increase exponentially, right? Because you just think of this as being made up of different phase points. Each of those phase points is following a well-defined trajectory. And so those phase points are going to diverge in this way. So the width is going to increase as a function of time as h bar e to the lambda t. And when this gets to be of order 1 in some units, that is when you can no longer really in any way talk meaningfully about the separation of two trajectories which are very close to each other, because each individual trajectory itself has now spread to be of order 1. And so that time scale, you can see from here, is going to be something which will go as 1 over lambda times log of 1 over h bar, right? Sorry, did I get that right? Yeah. And let me just put a mod here. Okay. And so if your h bar is 0, then of course this time scale is infinity, meaning that then if you have no uncertainty, then you can basically keep distinguishing between these two closely spaced trajectories out to infinite time. But on the other hand, if you have a finite h bar, then you can see that this time scale is so there's a fixed time scale, and it's only meaningful to talk about these diverging trajectories up to that time scale, beyond which there is no divergence that you will see anymore. And that is the time scale that you see there. Okay, so this is something that's called the Ehrenfest time. So this is called the Ehrenfest time. And this is purely quantum mechanical. This is the time scale after which your OTOC saturates for a quantum mechanical system, and it actually has this dependence on h bar. So if you look at what you see here in this inset, so this is the OTOC divided by twice t. So remember that the log of the OTOC divided by twice t, and so that's going to be something like the Lyapunov exponent. And you are now looking at the Lyapunov exponent as a function of time. So if you look at this plot, and if you wanted to actually look at the Lyapunov exponent as a function of time, as long as you have this exponential increase, you have a constant Lyapunov exponent. And then once this thing starts plateauing, then of course the Lyapunov exponent defined this way is going to drop as a function of time, and that's what you see in this inset. So here you have a constant Lyapunov exponent till here, and then of course it starts dropping, and you can see that the time at which it starts dropping actually depends on this value of h bar. The larger h bar is, the longer the time up to which you see this exponential increase, the longer the time up to which you see a constant Lyapunov exponent. So that's here, and then as you decrease h bar, you can see that this time goes down, the Ehrenfest time goes down. As you increase h bar, not decrease, as you increase h bar, you can see that this Ehrenfest time goes down, consistent with this formula. And so that is a very important quantum mechanical effect. And so, if you read certain papers or books, you see language like the Ehrenfest time is the time beyond which a system realizes that it's actually a quantum mechanical system, where the effect of h bar kicks in. But the real message from this is that if you did want to extract a Lyapunov exponent for a classical system, for a quantum mechanical system, then you can't evolve the OTOC indefinitely up to long times. You will have to evolve it up to some finite time beyond which it's going to saturate. Okay? And you can also see that the smaller your value, the larger your value of h bar, the smaller this time is. So the larger your value of h bar, the smaller is the time over which you're going to see this exponential increase. And so for any system at very small times, in any case you may not see the exponential increase, even for some classical system. It's not like you see an exponential increase, an exponential divergence of the trajectories right from t equal to 0. So there might be some microscopic time scale up to which you don't see anything substantial, and then of course the thing kicks off and you have this exponential increase. So if your h bar is large, right, then the window over which you can see an exponential increase is going to be small, And if you make h bar sufficiently large, then you may not see any exponential increase at all. You may not see a Lyapunov exponent at all. So the message from this is that if you wanted to extract a Lyapunov exponent for a quantum mechanical system, it has to have some nice semi-classical limit. There is some parameter, there has to be some parameter which is the equivalent of h bar in the system, if not h bar itself, which you can set to a sufficiently small value, which you can sort of take to 0 in some way or make it very small, so that you have a sufficiently large region where you have this exponential increase of the O torque, and you can extract a Lyapunov exponent. So because I've run out of time, I'll stop here. So what I'll do in tomorrow's lecture is I'll conclude this discussion of Lyapunov exponents and the O torque by looking at systems with more than 1 degree of freedom. In fact, systems which are sort of more relevant to, say, study of proper condensed matter systems, again, spin chains and things like that, and look at what happens to the O torque for those systems which have many degrees of freedom. Quantum mechanically, what does the O torque look like? When can you extract a Lyapunov exponent? So it will turn out that for a spin system, there is the most natural way in which you can actually get to a semi-classical limit so that you can extract a Lyapunov exponent is to look at the limit of very large spins. So I'll first argue sort of heuristically that for a spin system, you don't normally expect the O torque to increase exponentially as a function of time, that you would actually expect it to increase as a power law. But as you make the value of the spin larger and larger, so if you go from spin half to spin 3 halves to spin 1 or whatever, spin half, spin 1, spin 3 halves, and you keep going, as you increase the value of the spin, you actually start seeing this exponential behavior. So I'll show you some numerical data. And in that semi-classical limit, even for a spin system, you can extract a Lyapunov exponent. And for spin systems which are not in that limit, I'll show you, what happens and how you can look at the O torque and what information it gives you. So that's going to be the plan of the next lecture. Okay. So thanks a lot. And any questions? Okay.
Yeah, so I have a question. So in that left-hand side plot, am I to conclude, no, the one on the top left-hand side?
Left, you mean right-hand side, this one, or?
Okay, left from, yeah, this one.
This one, the one that I'm pointing at.
No,
this one here, yeah, okay.
Left from my side.
Sorry.
Okay, so lambda increases as k increases. The system, no, the T star.
Yeah. So lambda will increase as k increases because we know that classically there is a so it becomes more chaotic as the kicking strength increases.
And therefore TE decreases.
So therefore you're talking about this. TE, yeah, because TE does also have a dependence on lambda.
And
right, yeah. So here the dependence of TE is the dependence on K because you're holding h bar constant, and you can see that as K increases, your lambda increases and your TE actually decreases. So if you look at K equal to 10, so these vertical lines are the TEs, and the shortest time is actually for the largest K. Right.
And what is this CGR? Quantum CGR?
Okay. So I forget what CGR stands for. If you look at the paper, it's something growth rate, correlative growth rate, or whatever. But CGR is really this exponent lambda tilde, which is the one that's extracted from calculating the square of the Poisson bracket, as opposed to obtaining Lyapunov exponents for individual trajectories and then averaging, which is lambda. Okay, thanks. Yeah, sure.
So when you say that this saturation behavior is strictly quantum, do you mean in terms of this only correlators?
Do I mean in terms of?
Do you mean in terms of these correlators, or in classical language it would be Poisson?
Okay, so yeah, so I mean in terms of the O torque that I defined in terms of the commutator saturating as time increases.
Because I would expect that if you are in the classical context and you just plot the d, the distance, it will also saturate eventually.
Right. But the point is that that's any saturation. Look, you can have some saturation because of some finite size.
Yeah, it's not quantum effect.
Right. So the important thing here, which of course these plots don't show you, is that the time at which it saturates is independent of Hilbert space dimension. Like here, this is not a system with any length scale in it, right? So if you wanted to impose some kind of a classical cutoff, it could be like, cutoff in energy or something, which would be like in the quantum mechanical case, the Hilbert space dimension. But it turns out that the TE that you get is independent of that Hilbert space dimension. So it's not saturating for the same reason that the OTOC of a classical system would saturate. This is just fundamentally dependent on H bar. Yeah.
So if, for example, in a disordered spin-off system where I do not have a semi-classical limit, a clear semi-classical limit, there also I can calculate this OTOCs, right? I can just take some operators. So can I substitute this 1 by H bar as the Hilbert space dimension?
For a disorder, no, okay. So remember that at least in the argument that I gave you, the H bar is showing up because I'm sort of insisting on using a classical picture even though the system is quantum mechanical, and then I say the best that I can do in terms of representing a phase space point is to think of it as a blob, and the size of that blob is some H bar, okay? So if you now wanted to do the same thing for a spin system, then things are complicated on different levels. So first of all, even if you think of a classical spin system, right? So the variables, the different spin projection, the different components of the spin in different directions are actually not canonically conjugate to one another, because the Poisson bracket relations between them are not like the Poisson bracket relations between position and momentum. So you can't even classically really think of a phase space for a spin system in the same way in which you would think of the phase space for this. So it turns out, and I'll show you this tomorrow, that if you take a quantum mechanical spin system of the sort that you're talking about with spin halves or something, then you don't even really have a region of exponential growth anywhere. You actually have a region of power law growth, and we'll see where the power law comes from. And then it does something funny and saturates, right? You will see, and you start seeing exponential growth only when you increase the value of S indefinitely. But there again, I'm not very sure if when you do that, you can actually, for the Ehrenfest time, replace this H bar by 1 over S. That's what you're saying, right? Can I think of H bar as 1 over S? So I'm not very sure if that necessarily works there. And so the short answer is I don't know whether the Ehrenfest times in those cases actually end up being proportional to something like log of S. Maybe not. Yeah.
So this correspondence that you made a statement about.
Yeah, say louder.
The correspondence that you made a statement about that an ensemble of states could give an answer which is similar to a generic answer given by a generic state. Is this like, does this become stronger as you increase the dimension of the Hilbert space that you are?
Well, actually, not really. Okay, so one way of looking at this is that, one simple way of looking at what I said there is that even if you just think of, let's say, a single particle in one dimension, right? And you think of some particular wave function for that particle. So if you take some wave packet, some Gaussian wave function or something, then of course the particle has a certain distribution for position and a certain distribution for momentum. So already even at that level, if you insisted on representing this quantum mechanical state in a classical phase space, you would need a blob, right? And so that's really what this is. And also similarly, when you're calculating the OTOC in some state, and you can use a single state as opposed to using an ensemble, it's again a similar idea that a single state would, because it would give you a distribution for the classical variables for position and for momentum, it's like you're already using a distribution even though you have this a single quantum mechanical state.
Is there any more questions? Okay,
Okay, thanks.